is given, like 2 raised to 11,213 minus 1. It will be always very difficult to find out that particular number. Therefore, nobody will be able to solve it. Nobody, in the sense that by chance you get it, that you get it, that's all. Otherwise, you will never get it. So for cryptography, the prime numbers are very good too. And these are the 7 problems that I was talking about. You can just visit the website of Clay Mathematical Institute, which gives us all this description about these problems. In that 5th problem, that Poincare conjecture, that was solved by Perelman. And the 6th one, that is Riemann hypothesis, that is related to the prime number. So, pardon? Yeah, zeta function. Yeah, that's right. It is related to the prime number. So, if you are interested in number theory part, you can just try that to get the solution of it. It is given in Clay Mathematical Institute's website. Yeah. Every solution of zeta number. Yeah. See, Riemann hypothesis deal with this particular zeta function, which actually says the distribution of the prime numbers. Now, if I give you a value of n, sit down. Can you give me the nth prime number? Is there any equation to obtain the nth prime number? I hope the question is understood. I give you a value of n. Is there any equation which gives us the nth prime number? There are no equations available. There are no equations available to obtain the nth prime number. Again, I think that can be again tried for it. Usually we don't, usually there is no equation available. But one thing we know is that the distribution of prime numbers is related with a particular number which we call it as E. E is that number which you said as an irrational number. E is the number which is related to the distribution of the prime numbers. That is dealing with the Riemann hypothesis. Now, non-Euclidean geometry, I will go to the next topic, because if there is time, we'll come back to non-Euclidean geometry. But what is the difference between Euclidean geometry and non-Euclidean geometry? Yeah.
In Euclidean geometry, there is study only on line, number line.
Okay.
And non-Euclidean means its coordinate axis to x, x, and y.
Okay. So anybody else? Non-Euclidean geometry. Your name? Abhishek. Okay, Abhishek.
Euclidean geometry only confines to 2 dimensions. Non-Euclidean goes to 3 dimensions, and in Euclidean geometry, it states that 2 lines, if they are not parallel, they will intersect.
Yeah. That's 5th postulate of Euclid. But non-Euclidean geometry is not confined to 2 dimensions. Have you heard of general theory of relativity?
Yes.
Who created it? Einstein. You know the geometry that he uses? It is non-Euclidean geometry, and he has 4 dimensions in that. That is 3 for space and 1 for time. So it is not a 2 dimension, it is a 4 dimension thing. So the main difference, in a simple way, if you want to say, in Euclidean geometry, the distance between 2 points will be always a straight line. In usual, for example, usual space you consider, you take any 2 points, consider the distance between them. Which will be the shortest distance between them? It will be a straight line. But that is not always true. For example, if you take the surface of a football, let us assume that a football. Now take any 2 points on that football. What will be the least distance among them? Yeah, it will be the chord joining. In fact, that great circle that comes into picture. So it is not the straight line, it is the chord joining those 2 points through that surface. That's what non-Euclidean geometry is. But in Euclidean geometry, the shortest distance will be always represented by the straight lines. Okay, we'll come back to if there is time for that. Talk about a simple experiment which gave a wonderful result. A simple experiment, very simple experiment in the sense it is just an observation. Now you recognize this picture. Jupiter with the moon. I thought it was Io. Io. There is a moon of, it's a moon of Jupiter, Io. It is the moons that Jupiter has. Now in the 17th century, it is in the 17th century, not even now. In the 17th century, a Danish scientist, Romer, his name was Romer, he looked into this observation. The observation was, he calculated the time that this Io, the planet, went behind the Jupiter and it passed through the shadow and come out on the other side. Okay, I hope you are following it. The moon Io, it enters into the shadow of Jupiter and complete that half the rotation and come out on the other side. He calculated the time for that. And when Jupiter was in another position, again he did the same experiment. Now this, I just now if you consider the green one as Earth and the blue one as Jupiter, and of course the center, the Sun. As Io passed through this, he calculated the time at this position when the Jupiter, and when the Jupiter is on the other side, that is, you see, the distance between Jupiter and Earth is much more compared to the earlier case. Now, if the speed of light was infinite, will there be any difference between this time? If it was infinite, there won't be any difference between this time. But what, to his surprise, he saw that there was a difference. Now, if there is a difference, then that says the speed of light is not infinite, it is finite. Now, he calculated the time. Now, AU means it is astronomical. Now, what is that one unit of that? It is it's the distance, average distance between the Earth and the Sun. So, what is that extra distance traveled by light in this case? Now, here we have one situation where he measures the measure from the Earth, and here there is another situation. So, what is that extra distance traveled by the light? 2 AU. It will be 2 AU. The extra distance traveled is 2 AU. So, from that he could make that calculation. Now, he saw that the difference was 20 minutes. 22 minutes. The difference in calculating that Io's time was 22 minutes, and the traveled distance of the light was 2 AUs, and which approximately came to 2.12 into 10 raised to 5 kilometers. 2.12, you can understand that there is plenty of error in this. Now the actual actual velocity is 3 into 10 raised to 5 kilometers. But you see that in the it is 1676. In the 17th century, he could make such a calculation to obtain the speed of light just by observing. See that important. Just by observing, he could make a greatest discovery of the science. Now later on, of course, the relativity, everything came based on this finite velocity of light. Okay. Now this is the, I suppose it is his photo, but that given, there is an actual paper published by him is given in that particular page. Okay, now here I give you two problems. Now problems in the sense, in physics or chemistry or even any ecological model, what happens is that you try to create a model of them and then try to solve it using mathematical equations. It can be differential equations or algebraic equations, such equations. Now, this is the problem related to parachute, if one lands using parachute. The first equation, you may not be aware of the derivatives, it's okay. The first equation actually represents the model of this landing problem, parachute landing problem. where m is the mass of the person, g we know it is a acceleration due to gravity, k is a constant, v is the velocity, and the solution is given by in the next line, that is v is equal to g by a multiplied by that part. Now here v0 is known as the, usually v0 we call it as the initial velocity. Now this is the final velocity with which he lands. V equal to that given equation, the final velocity with which he lands. Now from that solution, can you make any deduction already from that solution, given solution? Do we need to use both the terms? Or one, can we skip one? Now the second term, it is V0 multiplied by e raised to minus 80. Now what will be V0 usually? Zero. Initial velocity will be 0. So that first part itself you can just avoid that in the usual cases. So now we are dealing with only two terms. I mean only one term, that is g by a multiplied by 1 minus e raised to. Okay. What is the speciality of this exponential function in terms of derivatives?
It remains the same. There is differentiation. It's the same.
Same. That is the only function where the derivative remains the same function you get. Okay. Now, you talk about exponential growth and all. What it means exponential growth? Increasing very fast. If you say increasing very fast. But when you say e raised to minus 80, it is actually 1 divided by e raised to 80. Now, as time goes on, what happens to 1 by e raised to 80? Decreases. And it almost goes to 0. So that means you can also get rid of e raised to minus 80. So what is the solution? G by A. Now G by A is always a finite quantity. G by A is a finite quantity. So the fellow will be landing with finite velocity. So that's how the parachute helps people. Okay, the next one. Launching a satellite. Now I have written that equation in terms of E. Now usually, what are the geometrical figures that we have? Usually, geometrical figures. You have circle, then ellipse, parabola, hyperbola, straight lines. The usual geometrical paths are this one. Now how do you differentiate among them? These 4 or 5 geometrical shapes. Eccentricity. As you said, eccentricity. Now E is the letter standing for the eccentricity. Now if E is 0, what is it? Circle. Between 0 and 1 you have the value of E, it will be ellipse. It will be ellipse. E equal to 1? Greater than 1? Hyperbola. These are the way we differentiate the geometrical figures using the value of E. Now, if you want to launch a satellite, or say you want to go to outer space, there are two ways. One, you can select closed circuit. The other one, you can select open one. Now, closed one in the sense, it will, like if you send a satellite, it is supposed to go around Earth. Now there are two shapes using which it can go around Earth. One is circle, the other one is ellipse.